Okay, so I hope you are here. Now let us continue with lecture 40. So here my goal would be to introduce you to statistical inference. It's quite an applied area. So statistical inference can be used to make an inference from some sample data from a large population. Okay, so in this case, let us say we take an example of elections that happened in US. Okay, so recently we had we have seen election between the contest between Biden and Trump, and there is something called exit poll. Okay, so if you know this, so exit poll, usually they take some sample, and based on this sample data, they try to predict. Okay, and this is something that happens also in the Indian elections. So in this figure, we will see that so here we have the blue Biden, and then this red one is the Trump, right? So this is a statistic on the according to the gender. So if they are men, then a man, then what do they prefer? So so let us say 48% prefer Biden, and then 49% prefer Trump, and then if it's women, then 56%, 43%, and then they had a lot of these data. Okay, so like white and then black, and then Latino, what do they prefer, and so on. Okay, so all this, where if you see this here, they did this on some sample size. Okay, so this is 15,318. Okay, so and also here you can see college graduate and non-college degree and so on. So data has been collected on 15,000 respondents. So this corresponds to the sample size, and based on this statistic was made. So it's obviously it did not contain all the population, but only some sample population was taken. So and moreover, all the figure have a margin of error which is wider for smaller subgroups. Okay, so there is some margin of error which you can see. These are the error which is noted in gray. So if you add this, it's not the case that you will have 100% all the time. So in this case, you will see that it's 94%, and then remaining part is an error. So it could be like 31 plus the remaining 6%, or it could be 63 plus the remaining percent. Okay, so this kind of data you will see a lot when you are dealing. So when you're dealing with, let us say, one familiar thing is election, and then newspapers come out with all kind of data. And so today's class will be on this. Okay, so how do we do some good inferences on based on some sample data? Okay, in this case it was like 15,000 odd data. Okay, and there are a few things to consider, right? So first of all, of course, our predictions should be very good, and then the second is it's a equivalent thing to say that the error should be less, or we should provide some bound on the error. Okay, so or we should give some confidence. Okay, so there is something called confidence interval. Okay, so we will see those things. Okay, and recently we saw we also had elections in India in the state of Bihar, and here you have seen the exit polls. Okay, so this is called poll of all polls. So so there were many exit polls in this case, and then finally you had the poll of all polls. So you take some kind of average of these polls. Okay. So in this case, there is one party, NDA, there is another party, Mahagathbandhan. So, and then there are other parties, LGP, others, and so on. And then these were the projected seats. And then, okay, obviously they were different because they each of them considered different sample, perhaps different sample sizes. and different kind of population maybe. Okay, so there are variations in this. So in other words, the sample were random. Like we are assuming that it's random data, right? So if this guy John ki baat, if they did this, then they might have taken they took a random sample. Like not all of them took the same fixed sample, right? So that's why we observe these variations. So there is some randomness involved here. Okay, and then yeah, so we get this, and sometimes we say quite a big variation here, right? So here it's quite a big variation. It's only 80 and then 50, 150 for this party and so on. But more or less one pattern what we saw is that they seem to give this party always always have a higher number of projected seats compared to this party. Okay, so so what we observe is that although they were independent polls, but then we do see some variations and so on, right? So how do we make a proper understanding of data like this when we know that there is some randomness involved? Okay, so how to do a correct estimation of this, and then you will see that when the results came. When the results came, these are the results for the poll. I mean, not the poll, but the actual elections. And then the election results went like this, where you can focus on this term. So these are the ones that are indicated here. So these were the two major parties in opposition. So if you see compared to this, the actual results were 125, but none of them gave 125 here. But here it's 110, and then most of them gave at least 120. All of them gave at least 120 here. And also, according to this exit poll, this party should have won. Okay, Mahagathbandhan should have won because you expected that so many polls happened independently, and wide variety of random sample might have been collected, and then we would have expected this to get 120, and which would have been good enough to form the government. And here we thought it's going to lose, right? So we saw that the things can change, right? So can you provide some estimate on these things, right? How confident you are of these projections and so on, right? So these are all statistical questions. Okay, so what do we observe from here is that it's about making sense of the data. So there are many things that we have seen already. So it could be like mean, variance, standard deviations, and so on. So those things also tell us something about the data. So that's the statistic part. But then sometimes what we want is that we want to infer from some sample data. Okay, not necessarily all the data is available to us. So we are not going to go to every house and ask whom did you voted for. Okay, so that's not possible in a large population. So sometimes what is essential is that we take some sample, and then from that sample we have to predict, make an inference. But then when we are doing that, we have to be confident about that. Okay, so or provide some error margin. Okay, so with this motivation, I can define statistical inference. So statistical inference is a collection of methods that deal with drawing conclusions from data that are prone to random variations. Okay, so drawing conclusions from the data, or in other words, inferring. Okay, inference is like making conclusion, right? So drawing conclusions or making an inference from the data, and by data I mean a subset of the data. Okay, so it's not possible to take all the data most of the time. So so that are prone to random variation, and they are prone to random variation. So they are the data, the sample that I'm taking, okay, is random. Okay, so they are not fixed. And of course, like when we are thinking about elections, things can change also, right? So you may take a poll before the elections, and then after 1 month the voter might change also, right? So there is some randomness involved here also from the voter point of view. Okay, so in this case, since there is expected to be a random variation, knowledge of probability is used obviously, and we need to work with the real data, and distribution of the data also may not be known to us. Okay, so distribution data may not be known because the way we are, it may happen that we are only going to the young voters. Okay, so then it's not representative of the true distribution. Okay, because the distribution is over the women, old people, and then between that also like gender bias could be there and so on. So so statistical inference is about is a topic where you take some sample. So in this case, this is the sample. Okay, and then you have certain hypotheses, and then you have certain methods to make some conclusions based on this sample, and then you conclude about the whole population. Okay, based on just this sample. So that's the topic of statistical inference. Now, there are two major types of statistical inference. One is called frequentist approach and one is called Bayesian approach. So the statistical inference, we will come back to this more later on. So a statistical inference problem itself we can define. So it's about determining an unknown quantity. To determine an unknown quantity, to get some data, just like I shown here, and then estimate the required quantity using the data. Okay, so that's what I explained here. That is called statistical inference. Now, as I said, there are frequentist approach and classical frequentist or classical. Okay, so they are classical inference. So a statistical inference problem is to estimate an unknown quantity from some data. Okay, that's we are just recalling that. So here the unknown quantity. So now we are getting into the differences of frequentist and Bayesian. So unknown quantity is assumed to be a fixed quantity and not random. Okay, so here the quantity that we want to predict is assumed to be fixed. Okay, although we are predicting it from a random sample. Okay, the data itself is random, but the quantity that we want to predict is fixed. Okay, so the unknown quantity theta is to be estimated by the observed data. Okay, obviously. So let theta be the percentage of people who will vote for a given candidate. So the theta that we are assuming that it's some for some fixed quantity that we want to predict. So, and in this case is the percentage of the people that will vote for a given candidate. So we can provide our estimate for that. Okay, so if y is the number of people that were randomly chosen and who will vote for the candidate. Okay, so you have collected the data of size n. Let us say there were n people. Out of those n people, y number of people said that they are going to vote for the candidate. So the percentage will be y divided by n. Okay, so that's like the frequentist approach, right? Because here it's about counting, right? So that's the frequentist based approach. So although theta is not random, we estimate it via theta hat, which is a random variable. Okay, and here theta hat is a random variable because it depends on the random sample, because the samples that we chose were collected randomly, right? Okay, now so that was frequentist approach. Now we come to the Bayesian approach, Bayesian influence, which, as I said, there are two major types. So what is Bayesian influence? Here the unknown quantity theta is assumed to be a random variable. Okay, that's the difference. Okay, so furthermore, we assume to have some initial guess about the distribution of theta. So as we observe the data, we can update the distribution of theta using the Bayesian rule. Okay, so for instance, let us consider this example. Consider communication systems in which the information is transmitted in the form of bits. In each transmission, the transmitter sends a 1 with probability p and sends a 0 with probability 1 minus p. Hence, if theta is the transmitted bit, then theta, of course, in this case, bit transmission 0 and 1 with probability p. Okay, so then we know that it's a Bernoulli. And let us assume that at the receiver end, we get the output x. The problem now is to estimate theta from the noisy output x. Okay, because there is some probability involved in involved in so which output X we are going to expect, because there is some probability involved in the bits. So in this case, the theta is going to be from a noisy output X. Okay, so we use the prior, and in this case we are also going to use the prior knowledge with that theta was given to be Bernoulli. Okay, so that's the prior knowledge is already known, given to us. Okay, so we will come back to the Bayesian inference a bit later. Let us get into the classical inference, and then we will do the Bayesian inference with more detail. Okay, if you don't understand it now, it's fine. You can come back to it later. Okay, so first step in a statistical inference is the computing the sample, right? So we will now precisely say what is a random sample. Okay, what do we mean by a sample, right? So this is a population, and then we want to take a random sample. So consider a random sample of size n. So let us say x1 to xn. So n samples we have chosen. So n samples. And we also consider with replacement. Okay, so there is a reason why I will do it with replacement. Okay, you can say that with replacement is not a good sample, because I may repeat the person. So I pick a person from here, and then I put it here, and then I put that person back, and then I draw another sample back. So you may say that this may not be a good idea, but I will explain this a bit later. Okay, why with replacement is okay. So consider that you pick people, and then one, and then you put it back, and then you pick another people and put it back. And obviously, like in theory, you put it back, but then that person is still here in your sample. Okay. Okay. So we choose a person uniformly at random from the population, and let x1 be the height of that person. So for an example, let us say it's about the height. So I took this guy and then measured the height and put this guy back. But I have the data for this guy. Okay. So essentially that guy is there in my sample. So here every person in the population has the same chance of being chosen. So there is no bias in which person I'm going to choose. Okay, so that is assumed. Now to determine the value of x2, again we choose a person uniformly and independently, obviously. Okay, so let us say you are blindfolded, and then you just pull out some person from there. Okay, and let x2 again be the height. So again, every person in the population has the same chance of being chosen. In general, xi is the height of the ith person that is chosen uniformly and independently from the population. So now we come back to the question of why with replacement. Well, if the population is large, then the probability of choosing one person twice is extremely low. So first of all, we are saying that practically it's fine. It's very rare that I'm going to pick the same person again and measure the height, and then I get the duplicate heights. So that's not going to happen that often. Okay, especially if the population is very large and you are doing things uniformly and independently. It's very rare that the same person will be chosen twice. Now you will say, still, why do I do it with replacement, right? So that's because I want to maintain xi to be independent. Okay, so I want to make the same probability of them picking out. So if I pick them out and then I put them back, then the independence of these variables is maintained. Okay, otherwise if I put that out, then it's no longer dependent, because it's conditional on the fact that I have taken out one guy, and then out of the remaining ones I'm going to pull out the samples, right? So there are two major things here. Okay, so it's like we don't want to disturb the distribution of the population by not putting these samples back, because it may happen that the distribution might get changed. Okay, that's one. And also we want to keep the independence. Okay, so in other words, what we really want is identically and independent distributed. Okay, and the reason why we do this is that this makes our analysis simpler, and the theory that we want to build for the statistical inference, and that will be simpler. But on the other hand, we also know that practically it's fine because the population is assumed to be very large. Okay, so perhaps you are not supposed to do this, apply this statistical inference theory that we are going to discuss on very small population. Okay, so we are going to do it on large population, and then these things will be maintained. And assuming this, then many things will be developed. So now we can concretely define a random sample. So the collection of random variables x1 to xn that you draw from the population, it's said to be a random sample of size n, okay, because you have pulled out n of them. If they are independent and identically distributed. So any sampling that you do, if it is independent and identically distributed, then it will be a random sample. In other words, x1 to x3 are independent random variables and they have the same distribution. Okay, that's the meaning of identically distributed. And since they have the same distribution, so these things are now implied that the CDF for a given x, they will produce the same values for all given x. Okay, now now we get into the estimation part. So what are the things we can estimate from the samples? Okay, so we will be working most always with the sample, not with the whole population. So let x1 to xn be a random sample. So they are IID. Okay, so that's given. So x1 to xn are random variables IID, and hence the following hold truths. They are independent, and then CDF is the same. Okay, and expectation will be the same because they are the same distribution. Variance will be the same because they are the same distribution. Okay, so these were just the properties of the random sample, and the sample mean we can define. I have discussed this before. Sample mean is the same definition here. So basically you do x1 plus xn divided by n. So that's the sample mean, right? So we have discussed this when we were discussing like law of large number, right? So there we did this. Okay. So now let us see some properties of sample mean, right? So expectations and of the x bar. So x bar here is the sample mean, right? So that remains mu due to the linearity of expectation. If I do, so there will be n mu on the top and then n, so n get cancelled and I will get back mu. And similarly, we have also shown this before for sample mean. We have proved this before. And these are just things we are recalling. What are the things we know about sample mean? Well, we know weak law of large numbers. So this is something we know. So as n tends to infinity, we know that the sample mean will start approaching the true mean. Okay, the probability that's so of the sample means going close to the true mean is very high. Okay, and we also know central limit theorem. So this is how we construct using the sample mean. And so we take we scale by the mu and the variance and so on. And then we know that Zn as n tends to infinity starts behaving like a standard normal distribution. In other words, the limit n tends to infinity is given by the standard normal. Okay, so a standard normal. Okay, so okay, so these are the things we have recalled sample mean. We have recalled the properties of sample mean, which are like weak law of large numbers, central limit theorem. Now we study something. Now I introduce something called order statistics, and it's PDF and CDF. By order, you can guess it's about ordering, right? So it's like, can we order the samples, right? So can we order the sample? If that is the case, then what will be the PDF of the minimum, maximum, intermediate ones, and so on? Okay, so let me define it. So let x1 to xn be the random sample from, let us say, some continuous random continuous distribution with CDF fxx. If we order the random variables from smallest to largest, in other words, I order them like this, then obviously x1 I will define is by the ordering itself is minimum of these random variable, and xn is the max of this random variable. And here the xi is called the order statistic. So now if I say 2, then it will be the second of this, right? The second largest. So you can define ith random variable as the ith like the ith in this case is like the ith smallest. Okay, so ith smallest. So since I start from here, so ith smallest random variable, because I know the ordering, so I can pick out which is the ith smallest. That will be the ith random variable according to this ordering. So in that case, I will not prove this, but then CDF and PDF can be found to be like this. Okay, so CDF will be given like this and PDF will be given like this. and the joint PDF of these random variables will be given by this. Okay, so it's just a expression that we, yeah, I mean, for the moment I'm not going to prove it, but this is the PDF and CDF. We claim that we know this for the ordered random variable. Okay, and there is some let us say some example on order statistics. So let x1, x4 and variable for the uniform distribution, and let be the x1, x2, x3, x4 be the order statistics. So usually we start with a random variable like this, and then when we say order statistic, we put this in the parenthesis, right? So this is why it's then we call it order statistics of x1 to x4. Then find the PDF of x1, x2, x4, and so on. Now this is trivial, assuming that what we have from here, right? So this will, because it's about order statistics. So to compute that, I have the formulas like this, right? So I can immediately use that, and then to write the order statistics. So for example, if I have to compute the order statistics, so just for one example, I can write this as, let us say I want to do it for 2. So the PDF of that, okay, so I'm supposed to find the PDF. So this will be, yeah, so this will be this quantity n factorial by I minus 1 factorial n minus I. So n is 4 here, right? And 2 minus 1, okay, and then 4 minus 2, and then here I will have 2 minus 1, and then 4 minus 2. Okay, so that's the thing we have. So let me write down here. So there it was 4 factorial, and then 2 minus 1 factorial, and then 4 minus 2 factorial, and then fx x, and then fxx, the CDF, and then this is 2 minus 1, and then I had 1 minus fxx, and then 4 minus 2. Okay, you can leave it here. So obviously this is generic, so I can find out for all these. Okay, so that's very simple application of the previous. Okay, now what I will go. So what we saw in the last slide is order statistics, right? And what are the CDF and PDF? Okay, now we move on to estimators. So let us say, let me define a point estimator. Okay, so point estimator. So let theta be the unknown parameter to be estimated. Okay, so some parameter that I want to estimate. It could have been mean, it could have been some variance, whatever. Okay, there are any useful information that I want to predict. So for example, let us say theta is expectation of x. Now let x1 to xn be a random sample. So implies that they are IID, which we want to using which we want to estimate theta. So using this sample, we want to estimate the average of the whole population, right? So here xi's have the same distribution, so that's what we know. Okay, because they are random samples, obviously. So to estimate theta, we define a point estimator of theta hat as follows. So this is how I define a point estimator. So the reason why it's called point estimator is because I get the estimate by putting point-wise values of x1 to xn random variable. Okay, that's why it's point estimate. So there can be many possible point estimators. Because I have this now generic function h, it seems like I will have many possible point estimators, right? So the question is like, which one is the good one to choose, right? So for example, if theta, the estimate that we want to do is for the expectation of x, then the point estimator we choose is h, which is defined like this. So h of x1 to xn is defined as sum of x1 to xn divided by n. So this is one possible point estimator. Okay. So a natural question is, there can be many possible point estimators. So which one to choose? So we need some parameter. Based on that, we can say that this estimator is good and that estimator is good, and so on, right? So we need a way, measurement, a measure to know which of the estimator is good. So one thing would be is to define something called bias. Okay, so I will define this. So the bias of a point estimator theta hat will be defined as as follows. So bias is defined as expectation of theta hat minus theta. So like what do you expect from your theta hat? Okay, your point estimator, and is this matching the quantity that you actually wanted to estimate? So on average, like does your estimate hold good, right? So or does it match the quantity that you want to estimate? So what do we interpret from here? Well, if the bias is close to 0, then we expect. Okay, we expect, right? So if the bias is close to 0, then theta hat is close to theta. That's what we are expecting, because we are saying that, okay, on average, because expectation is like on average. So on average, if my estimate is close to theta, then maybe my point estimate is also close to theta, is closer to theta. So we say that theta hat is an unbiased estimator for a parameter if the bias is 0. If the bias is 0, then we will say that it's an unbiased estimator. Okay, it's unbiased estimator. So that's the definition. So then we say it's unbiased estimator for all possible value of theta. Okay, and but here is the fact, right? So that an unbiased estimator is not necessarily a good estimator. So unbiased doesn't necessarily mean that you have got hold of a good estimator. Okay, so why is that? Right, so unbiased estimator is not necessarily a good estimator. So let me give you an example to you to prove this claim that why unbiased doesn't necessarily mean that you have a good estimator. So let us do this proof. So let x1, x2, sorry, here I mean x2, okay, to xn be a random sample. So random sample. And the sample mean we can define as theta hat is x bar is x1 plus x2 plus xn divided by n, right? So this is how we define a sample mean. Now, if we choose, let us say theta hat as, let us say theta hat 1 as x1. So this is some another estimator. So this is some estimator that I have chosen. So this is another theta hat. Okay. Now I want to know, is this biased, unbiased, whether this is a good estimate or not, right? So then let us check for this theta hat. Then theta hat 1 is also an unbiased estimator of theta. Why is that? Because if we compute the bias of theta hat 1, then this is so theta hat 1 was just x1, right? So but let me first write down the formula for the bias. So theta hat 1 minus theta. So this is, so theta hat 1 was x1, so this is x1 minus theta. Now expectation of now the expectation of x1, okay, is also theta. Okay, so it's theta minus theta, so that's going to be 0, right? So what do we observe from here? We observe that x1, because it's like independent and identically distributed, so they have like the same mean. Remember that theta was expectation, right? So x1 also is theta, right? So that's why we got this. So what we observe is that even this estimator is giving me, it's an unbiased estimator, right? But intuitively we know that just x1 is not a good indicator of the mean, right? So what do we observe? So observe theta hat 1 is probably not as good as sample mean x bar. Okay, so ideally the mean would be better if I take the mean like this, where I take more and more samples, and then I I take the expectation of that and so on. Okay, so that is assumed to be a better, that we believe is the better estimate than then just taking the first sample. You may say that, well, isn't that the consequence of forcefully assuming xi to be IID, right? Because that's the reason why it became theta, right? So IID was a convenient choice, I would say. Okay, but so IID is a convenient choice to pick a random sample. But in practice, what might happen is that it's much better to actually assume n samples and compute average from there. Okay, so that's the thing we learn from here. Okay, so we need something more than just the unbiased estimator, because the way we have defined the random sample and so on, just unbiased estimator is not a good thing. Okay, so we need something more as a good measure of so we need other measures. So need other measures to ensure that the estimator is a good estimator, I mean, not in theory. In theory, we said that it's IID, right? And then you will say, oh, okay, then that's already it's, but not really, right? But in practice, we know that it's not going to be the case. So in practice, we want this to be computed from a significant amount of population and so on. Okay, so there are technical things we need to fix before for these cases. Okay, so let us see what we can do for this. So a better estimator is so-called mean square error. So this is theta hat minus theta squared. Okay, so we will see why this is a better choice. Okay, so now next I will define this quantity, and then you will see why this is better. Okay, so this is called mean square error. The mean square error of a point estimator denoted by Msc theta hat is defined as this. Now, if you define it like this, then this quantity will actually make sure that the unbiased estimator is also essentially a good estimator. Okay, so it will try to throw away those previous cases. Okay, so let us see how we can compute this. Okay, so let x1 to xn be a random sample from a distribution with mean theta. So as usual so far, so our parameter to be estimated is so far theta, which is the expectations, and the variance is sigma square. Okay, they are IID for all xi it's theta, and variance for all I is sigma square. Okay, now for the following two estimators of theta. So the first estimator, remember in the previous example, was theta 1 hat is x1, and the second estimator we chose was sum of x1 to xn divided by n. Now the question is find out what is the mean square error for the estimator theta 1 and mean square error for the estimator theta 2, and so that for n greater than 1, the mean square error for the theta 1 is higher. In other words, it's not a good estimator. Okay, then the second estimator. So second estimator error is lesser than the first estimator. Okay, so let us try to solve this, and then this will tell us why mean square error is a better choice. Okay, so so the solution is, so we have Msc theta hat 1 is expectation of theta hat 1 minus small theta and then squared, and this is expectation of, now theta hat 1 was x1 minus expectation of, so theta small theta I can write is expectation of x1. Okay, it's any xi, but we can write x1 squared, and this we know is nothing but the variance of x1, and this is, we know it's sigma squared. Okay, now to find Msc, now we move to the other one, right? So theta hat 2. So theta hat 2 is expectation of theta hat 2 minus theta squared, and now theta hat 2 was the sample mean, right? So the x bar. So this is x bar minus theta and then squared. Now this is so this I can write this as variance of x bar minus theta. Recall the formula, right? So expectation of x bar minus theta whole squared, right? So variance is the expectation of x square minus expectation x whole square, right? So that's what I have used, that variance formula. Okay, so this is what I have. Now what is the variance of a variable shifted by a constant is the same as the variance itself. Constant doesn't change the variance, right? Okay, I mean the constant as a translation doesn't change, right? So this is this, and then plus now we have expectation of x minus sample mean minus theta, right? So by linearity, right, we can apply linearity here. So expectation of the x bar is theta itself. So theta minus theta will be 0, right? So this will be 0. So this implies that Msc theta hat 2 is variance of x bar. Now variance of x bar we know is sigma square by n. Now we know this, right? So Msc theta 2 we know, Msc theta 1 we know, right? Now you compare this to quantity. So as n greater than 1, you know this one, right? So as n greater than 1, Msc theta 1 hat is a bigger error than Msc theta hat 2. Okay, and in fact, as your random sample size increases, the Msc error is decreasing. Okay, so that's a very good thing. Okay, but in this case, in fact, with a increasing population, it's not decreasing, because obviously your sample just took the first, and it's trying to infer from the first sample itself, which is x1, right? So that's why Msc is a good measurement to check whether you are having a good estimator. Okay, and it does decrease with increasing population size. Obviously, more and more data I take, better I will get at estimating. Okay, so now what is the relationship between Msc variance and bias? Let us see that. So what I claim is this. So Msc theta hat is nothing but variance of theta hat plus bias of theta hat squared. Okay, so we can try to do this directly. So the proof of this is that Msc theta hat. So we apply the definition. So what was the definition of Msc? So it was expectation of theta hat minus theta and then whole squared, right? So this was if we use the variance formula. So this is already we have seen in the previous example actually. So theta hat minus theta and then plus expectation of theta hat minus theta and then whole square. So this is something we have also applied before, and this is variance of theta hat plus, and this was nothing but the bias. Expectation of theta hat minus theta was nothing but the bias. So I can write this as bias of theta hat, and then there is a square here. So it's a square here. Okay, so that was the easy thing to prove. Now what we define is so-called consistent estimator. So consistent estimator idea here is that as the n is increasing, the random sample size is increasing, my estimates should become better and better. Right? So this is something we have seen for Msc, right? Msc we have seen that as n is tending, sigma square by n is tending to 0. Okay, so in that view, let us define so-called consistent estimator. So it's like theta1 is based on my some smaller observation, theta2 is based on slightly bigger number of observation, and so on, right? So that will generate a sequence of estimator. For instance, if in the previous example I took theta2 as like this, x1 plus x2 by 2, okay, and then theta hat 3 x1 plus x2 plus x3 by 3 and so on. Okay, so I can generate a sequence like this. If so, we say that theta hat is a constant estimator if the probability that theta hat minus theta is going to 0. Okay, so as n tends to infinity, theta hat is getting closer to the estimate that I want to do. Okay, so remember, theta, small theta, could be anything that I want to estimate. So far we have set it to be an expectation of the random variable x, but it could be any quantity of interest. Okay, so let theta1 to theta be the sequence of point estimators for theta. If MSE, if limit n tends to infinity, if the MSE of this sequence becomes 0 as n tends to infinity, then theta hat will be defined to be a consistent estimator of theta. Okay, so let us try to prove this claim, right? So so what we have to say that for MSE, if this happens for MSE, okay, if this happens for MSE, then we can claim this. Okay, so for so let us assume this, and then we try to prove this, right? So we can write, so probability that theta hat n minus theta is greater than equal to epsilon is probability that is the probability that theta hat n minus theta squared is greater than equal to epsilon square. So I can just follow from here. Okay, I can square both sides, and I maintain this. Okay, so this is, so this will be now I apply the Markov. So if I apply the Markov, theta hat n minus theta whole square divided by epsilon square. So this is due to Markov. Okay, so this will be, but this is nothing but MSE theta hat n by epsilon square, and then from previous thing we have sigma square by n square and then epsilon square. Okay, so that was the MSE. Now now this goes to 0 as n tends to infinity. Okay, because of the n quantity here. Okay, so this is what we know. Okay, so I mean, even if you don't write this part, right? Even if you don't write this part, let us say. So now you apply the limit on both sides. Okay, so let us not do this part. Let us say you apply the limit on both sides. So limit n tends to infinity is limit n tends to infinity, but this guy is given to be here, right? So this guy is here. So limit n tends to infinity, MSE theta n is tending to 0. So this overall is tending to is equal to 0. Okay, so you don't have to assume even this. So this is like generally you are given that MSE is 0. So then it satisfies the condition for being a consistent estimator. Okay. Okay, so similar to sample mean, we can go ahead and define sample variance and sample standard deviation. It's like variance defined on a sample, standard deviation based on a sample. So let x1 to xn be a random sample, okay, with mean because they are IID, so they are same, and variance is the same. The sample variance for this random sample is defined as follows. Now remember, sample mean was defined as x bar, right? And x1 plus dot 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 plus xn by n, right? Sample mean is defined in this way. Okay, so remember there is n minus 1 here. Don't get confused. Okay, so there are reasons why we should keep it n minus 1. Okay, technical reasons. It doesn't hurt basically. Okay, there is no big difference between n and n minus 1. Okay, they are for a large sample 99 and 100 doesn't matter that much, but there are some technical reasons where it's better to put n minus 1. And so just remember this that it's sum of the differences and then divided by n minus 1. Okay, and yeah, so we can just expand this. So if we expand this, then it will look like this. Okay, so is this correct? Because okay, so here yeah, n of this will be there, but then I hope it's because this is after simplifying this. I hope this is correct. Okay, we have to check that this is correct after simplifications, because there will be like n terms here, right? So 2n and then cross terms will be there and so on. Okay, but the cross term is missing here, right? Yeah, cross term is missing here, so I have to check this. But for the moment, we can also take this as a definition. Okay, so this simplification may not be correct. I'm not sure right now. Okay, so we can check that the sample variance is an unbiased estimator of theta square. So this is a check that we can do, that this is an unbiased estimator of sigma square. Okay, so this is something we can check it as an exercise. Okay, in other words, like the expectation of so this is our x square minus sigma square. Okay, so this is our bias. Okay, so this is like 0. Okay, so this is something we have to check. Why if we define our sample variance to be like this, then it's going to be 0. So that's a check that you can do later. Okay, so similarly, once we have a sample variance, then we can take a sample mean as a square root of that. And yeah, so and it is usually used as an estimator of sigma. Okay, so estimator of the standard deviation of the actual underlying distribution, right? So and also S is an unbiased estimator. So the standard deviation is also an unbiased estimator of the actual standard deviation. So these are the things you can verify, okay, by checking that bias. Okay, so let us see an example. Let T be a time that is needed for a specific task in a factory to be completed. In order to estimate the mean and variance of T, we observe the random sample. So let us say we have this random sample. Thus, TIs are IID and have the same distribution. So we obtain the following values. Okay, find the values of the sample mean, the sample variance, and the sample standard deviation for the observed example. Okay, so we are given the samples. Okay, so random samples of T1, T2, T3, T4, T5, T6 is given to us, and from there we have to compute the sample mean. So sample mean is very easy. So sample mean is just T1 plus dot plus T6 divided by 6. Okay, so this will be 18 plus 21 plus dot plus 20 divided by 6. So yeah, you can calculate this. And the sample variance is S square is 1 by n minus 1, right? So 6 minus 1. And then what was that? It was summation of Tk minus and minus this T bar, right? So T bar we have computed. So this, and then we have a square of this, and K is equal to 1 to 6. Okay, so this also you can compute. Okay, so sample and then standard deviation will be square root of S square. Okay, so this is a very simple example of how to compute sample mean, sample variance, and sample standard deviation. We can see another example. I have a bag that contains 3 balls. Each ball is either red or blue, but I have no information in addition to this. So there is a bag, okay, and there are 3 balls, and they are either red, blue, okay, red, blue. We just know that there are 2 colors, red and blue. So there are red and blue, but we don't know obviously which one is which. Thus, the number of blue balls, let the number of blue balls, call it theta, and it might be either 0, it might be either 1, it might be either 2 or 3. I am allowed to choose 4 balls at random from the bag with reflection. Okay, that's why we call it 4 ball, right? Otherwise, how will you pick 4 balls, right? So we can do it only with allowed to replace, right? So basically, I draw 4 samples. Okay, because I'm doing replacement, so I can draw 4 samples, although there are only 3 balls. So we define the random variables x1 to x4 as follows. So xi is 1 if the ith chosen ball is blue, and xi 0 if the ith chosen ball is red. We observe here that xi's are IID, and xi will follow a Bernoulli. Okay, so and after the experiment, we because they are like equally likely, right? So that's why we have to like divide by 3 here. After the experiment, we observe the values of xi as follows. So let us say we observe the values of xi like this. Okay. So first time I pick, and then so what was the xi? So if I have chosen ball is blue and I have chosen ball is red, right? So x1 is like the first ball is blue. Yes. Okay. The second ball is blue. No, it's red, right? So it's 0, and then first is 1 is blue, and then it's blue. Okay. So let us say this is the observation we make after we have taken 4 samples. Okay. So from the above, what we observe is that we got 3 balls and 1 red ball in our random sample. Now answer the following: find the probability of the observed sample this for each possible theta. Okay, so for each possible theta, remember the theta is the number of blue balls. Okay, and that is denoted as theta. Okay, so find the probability of the observed sample. So what is the probability that I will get this sample? Okay, for each possible theta. Okay. So and find the value of theta that maximizes the probability of the observed sample. Okay. Okay, so let us try to prove this. Okay, so this is the data we are given. Okay, so theta is the number of blue balls, and that could be, I mean, as such in the bag, it is known quantity actually. Theta is known. It's just that we don't know, right? So we don't know, but it's a fixed quantity once we go and observe, right? But since we don't have an idea of anything, it could be any of this, and then we are picking 4 balls with replacement, and then we have certain observations, right? So then the question is find the probability that the observed sample that the observed sample will be this if the number of balls were 0. Observed sample will be this if the number of blue balls were 1, and so on. Like some boundary cases you can already guess, right? If the theta were 0, right? So this means that the blue ball is 0, right? So the total number of blue balls in the bag was 0. Then the probability of this happening is 0, because at many places I said that I'm going to get the blue ball. Okay, so probability of this sample is going to be 0. Okay, and same thing you can like make an argument, right? So if the observation was that so if we know that there in advance that there is 1 blue ball, like what is the probability of this sample, right? These observations, there is 1 blue ball, right? So in this case, remember that there is a replacement allowed, right? So that's when the things change, because there is a trick thing now, right? Because originally there was no blue ball. So even in the first step, you don't expect x1 to be 1 at any cost, right? Because there was no blue ball at all. So how can you get even the first sample to be blue ball? But in the second case, if there is one blue ball guaranteed, then other two are red. So what might happen is this is possible now, because first one will be blue and I put this back because this is with replacement, right? So this is with replacement. So I put it back. And then the second one I draw is red because red is there. Okay, so two are red. And then since I have put the blue ball back, I can pull it back again. And then I can pull it, and then I put that ball back, and then I can pull out the same blue ball again. Okay, so this is this is possible, right? So there should be some probability of this observation, right? And similarly, we will have a blue. Let us say we have a two blue ball. Again, this is possible, right? Because yeah, it's possible because definitely because there is at least one red ball. So red ball is expected, and two are there. So and it's with replacement. So I can observe three blue balls as a sequence in the sequence, and then one red ball as well. And then there is a three red ball, but total are three. So this means that the red is 0 now, right? So red is 0. So in other words, like, can you ever get this case, right? You will never get this because there is no red ball at all. All are blue balls. So then the probability of this observation should be 0 again. Okay, so this is the observation we are making. So now we can write this concretely. Let us try to write this concretely. So solution here. So since first what we know is that xi is Bernoulli. Theta by 3. So what is the probability that I observe a blue ball, right? So it's Bernoulli, so it's like blue or red, but theta is the number of blue. So the probability that I get a blue is theta by 3. Okay, so this is the probability. So theta by 3 probability of picking blue, right? Okay, so now so since it is Bernoulli, we know the PMF. So since this is discrete, we talk about PMF. So this is theta by 3 for x equals to 1 and 1 minus theta by 3 for x equals to 0. So this is about blue. Remember, x equal to 1 encodes blue and x equal to 0 encodes the red ball. Okay, this is just encoding, right? Okay, so since xi's are independent, so since xi's are independent, the joint PMF is just a multiplication of the individual PMF. X4 is, so probability PMF of x1, x2, x3, x4, x1, x2, x3, x4 is the product, right? So probability x1, x1, x2, x2, x3, x3, and x4, x4 because they're independent. So product of the PMF, and therefore this okay, so here let me write down here. So this implies what, right? So probability x1, x2, x3, x4, and let us put the observation, right? So what was the observation? Observation we had was 1 0 1 1, right? 1 0 1 1. So this and this from the Bernoulli we know this, right? So Bernoulli would be theta by 3, first one. Second one is 0, so it is 1 minus theta by 3, the probability for the red ball, and then theta by 3, and then theta by 3 for the another red ball, another two red balls. So this is theta by 3 cube and 1 minus theta by 3. So obviously the joint PMF depends on theta. Okay, so now we know what are the possible values of theta, right? So possible values of theta are like 0, 1, 2, 3. So the number of blue balls, right? So we can construct a table of these probabilities for various values of theta. So let us make a table. So theta, if it is 0, if it is 1, if it is 2, if it is 3, then the PMF values x1, x2, x3, x4, 1, 0, 1, 1, and then theta, because there is also a theta here, right? So 0 case, we know it's going to be 0. That we have picked it on our own, but we can also do it from the formula itself. And then there is some data here. Okay, so I have pre-computed some values here. So 0 to was something I found, and then you can check this on your own by putting theta equals to 1, you get some value, which is this, and theta equal to 2, you will get this value. Okay, there are some more terms. Okay, so indeed the probability of 0 will come out to be 0, and then this come out to be for theta equal to 0 is 0, theta equal to 3 is 0. And so what was the question? Find the probability for each value of we have done that. So we have listed out the table. Now the question is find the value of theta that maximizes the probability. Okay, now maximizing the probability. So what? So from the table, what we observe, this is the theta that maximizes the probability, right? So theta. So in this case, we listed out all the values, right? And then from there we picked which theta equal to 2 maximizes the probability. Okay, probability of that observation, right? Okay, so this is interesting for data point of view, because what this tells us is like what could have been the yeah, so what could have been in my population, right? So that a given observation can be maximized. Okay, so this is like a reverse question we are asking, right? So the probability, we think like, what is the probability that I will get? What is the probability that I will observe something? Now we are asking in a slightly different way. We have observed something. Now, how could my observation the probability of my observation could have been better, right? What could I have changed in my sample space itself? Okay, so this is interesting, right? So this is like other way. Okay, so and what we have done in this example is that we have listed out, and then we have said, okay, pick the best and so on, because we have found a of theta parameter, and theta is telling us theta is a parameter corresponding to my sample space, and this is allowing me to change my sample space and or the population, and then from there I can maximize or minimize my observation. So this is a way we have handpicked, but then we can say that is there a concrete way to do this maximizations? Well, calculus will help again, right? So how do we maximize a function, minimize a function? We have seen this a couple of times in this class, right? Okay, so this leads us to something called, so here I have not done this. So let me, so theta, so called maximum likelihood. Okay, so this is called maximum likelihood estimate of theta. Okay, so theta equal to 2, we will call it as a maximum likelihood estimate, obviously for the given observation. If observation changes, then something else will be good theta, right? So we are going to now define something called maximum likelihood estimate. Okay, so first of all, likelihood and log likelihood functions. So definition of likelihood and log likelihood: let x1 to xn be a random sample from a distribution with parameter theta. Suppose that we have observed. Okay, so observation is made. If xi is a discrete, then the likelihood function is defined to be like this. Okay, so this is, we have seen in the previous example. This is the joint PMF, but parameterized by theta now. Okay, and so this whole thing is given a different name now. It's L of this. And then if xi's are jointly continuous, so in the case of discrete case, it's the PMF, obviously, and in the continuous case, we will replace it by CDF. Okay, so CDF in the continuous case. And again, we use the same notation. So from the context, we will know where to use PDF and where to use the CDF. Important thing is that they are parameterized by this theta parameter. In some problems, it is easier to work with log likelihood. Some problems it's easier to work with log likelihood because it will simplify. Because the thing is that log is, so if I'm trying to maximize a function, right? So if it is like an increasing function, then if I take a log of that is also an increasing function. But sometimes it can simplify, right? Sometimes it can simplify my way to compute the maximum. So that's why it's just a tool you can think of, that sometimes you will maximize the log of the likelihood rather than the likelihood itself. In some cases, it's simpler to do that. Okay, so finding a maximum of a log of a function is sometimes easier than the function itself. That's the idea here. Okay, and our whole point is going towards finding the maximum likelihood. Okay, so we have defined these terms, and so that's why we can say that log likelihood will be ln natural logarithm and this. Okay, especially if you have products like things like and then exponential of something. So log, if you take, exponential will go away and you get a simplified variant most likely. Okay, so let us do some example. Find the likelihood function for the following random sample. Okay, so find the, okay, so these are the observations we have, and we are given that it's a binomial, so NP. Okay, so it's known to us. And obviously when we are saying observed, we have observed 4, but there were only n. So all this is happening because of the replacement. I can have 4 samples coming out because I'm replacing also, although the total data is 3. Okay, and then this is the observation I make. Okay, and then another set of random variables are coming from exponential distribution, and then we have made an observation like this. Okay, so what is the find the likelihood function for the following random sample? So let us work with this, and we will. Okay, so let us solve for this likelihood function, right? Okay, so recall that random sample. So in a random sample, by definition, sample. So in our case, the random samples are what? X1, X2, X3, X4, R, I, D by definition. Okay. Now you see how this is IID is helping us most of the time, right? So these are IID. So this implies what? So this implies that the joint PMF and PDF is equal to product of marginal. Okay, we have done this multiple times now. Marginal PMF and PDF respectively. Okay, so this is like I should put this in the bracket. Okay, you don't have to multiply PDF and PMF together, right? So okay, so remember in the likelihood function we need a joint PDF, right? So joint PDF gives us the, so what was the definition of the, so joint PDF, this is what we want, right? So essentially it's about finding the joint PDF, that's it. Theta will just pop up, right? So let us see, theta will pop up because theta is a parameter of the distribution itself. So while I'm writing the marginal, the theta is there in the marginal itself, so it will show up in the product also, okay, in the joint. So if xi's are binomial, okay, in the first case, xi's are binomial, so this is 3 theta, then the marginals we know, right? So marginal is xi theta is 3x, okay, and then theta x 1 minus theta 3 minus x. Okay, so this is something we know. This is just the binomial, right, with parameter np, right? So n is 3 and p is x for us, right? Okay, so this is how the probability values are given. I mean the PMF, right? So you have to just remember the PMF. So PMF of the binomial is given by this, and hence the likelihood, I can write it here. So likelihood will be x1, x2, x3, x4. Theta will be the joint x2, x3, x4, x1, x2, x3, x4, comma, and then theta. And this is just the product of the marginals. So this is x1. Okay, so I will just write it like this without showing the arguments. X4, and this marginals we know, right? So marginals we know. So the observations we had was, so it is 3x1 and then 3x2. The other observations 3x3 and 3x4, and then theta x1 plus x2 plus x3 plus x4. And you can verify this. Okay, I'm writing this directly. 12 minus x1 plus x2 plus x3 plus x4. Okay, so this is the likelihood function. Okay, and since we have observed, since we have x1, x2, x3, x4 is 1, 3, 2, 2. And so we just substitute the values. So this implies L 1, 3, 2, 2. Theta is 3, 1. We substitute these values. So this is the PDF, right? So we substitute these values here. So 3, 3, 3, 2 here, right? So 3, 2, and theta to the 8, 1 minus theta to the 4. So this I have pre-calculated this value. So this is 27, theta to the 8, 1 minus theta to the 4 if you do this computation. Okay, so this is how you compute the likelihood, and same thing you can do it for the exponential. It's just that you have to replace the marginals of the exponential. Okay, so I'm going to skip that. Now we come, so we have seen likelihood. Now we talk about maximum likelihood. Remember that previous question on the balls, red ball, blue ball, and then we wanted to maximize and so on. So now we are going to the maximum likelihood estimator. So let x1 to xn be a random sample from a distribution with parameter theta. Given that we have observed this, a maximum likelihood estimate for theta shown by theta hat ml is the value of theta that maximizes the log likelihood. So basically we have to maximize this over all possible theta. Okay, so a maximum likelihood estimator for the parameter theta is denoted by this theta hat ml is a random variable. Okay, so this itself will turn out to be a random variable. Okay, so the theta hat, and it can be denoted like this, and whose value x1 to xn is given by theta hat ml. So you can substitute the values of x, and then you can obtain the maximum theta value. Okay, right. So so like observation is given to you, so this is known to you. So this is just a function of theta. And then obviously like you can maximize this over theta. Okay, and then you can keep the x now. Okay, so you can keep the x, then it will now become a function of x1 to xn, right? So if I see the previous example, you will see that xi's are involved and theta is also involved. If I maximize this function with theta, and then I get the value theta for which this is maximum, I substitute that theta here. Okay, and then theta is known, so now it becomes a function of only x1, x2, x3, x4. Okay, so that's what we are saying here. So theta hat ml will boil down to just after you have maximized this, so theta is gone. Now you can treat this as a function. So you substitute the optimal theta here. So theta after maximizing this as a function for this observation, then you can substitute it here. Okay, so and that is how we say it's theta hat ml. And since theta hat ml is a function of the random variables, it is a random variable. Function of a random variable is a random variable, right? Okay, so example of maximum likelihood estimator. So for the following examples, the maximum likelihood estimator of theta is, so let us say x is binomial and we have observed x1 to xn, and x is exponential and we have observed x1 to xn. So what is the maximum likelihood estimator? So this is from the previous example, right? So, and what we have observed, x1 to xml was 1322, right? I have not put this here, 1.23, and what was 3.32, and so on, right? So we have this observation here. Okay, and we are previously we found likelihood estimator. Now we have to find maximum likelihood, right? So what we have found so far is L1322 theta is 27 theta to the 8. This is what we computed before, right? And theta to the 4. Okay, so that's what we found out for this particular observation. So to find the maximum value, so we have to do del L by del theta is, so if I do a differentiation of this and equate it to 0, that's how we find the maximum, right? 8 theta to the 7, 1 minus theta to the 4, minus 4 theta to the 8, 1 minus theta to the cube. Okay, and then we equate it to 0. So this would imply, you can check that this will be 2 over 3. Okay, so theta. Yeah, so what is the maximum? So what is the value for which this is maximized? This is the value for which this is going to be maximized. Yeah, so in this case, this is the value for which this is going to maximize. If you can solve for this, then the maximum likelihood estimate, the maximum value of theta that I'm going to find is this. Okay, and remember that I have substituted the values of these guys here. That's why you don't see x anymore, right? Because I have put the values here. And similarly, you can also do it for this. Okay, so this question is about finding the maximum value of theta, and this is what I'm going to get. Okay. Okay. Okay, so there is one more example of a maximum likelihood estimator. So in this case, it's like the standard normal, not standard normal, but just normal, the theta 1 and theta 2. And then this is the PDF is given for normal distribution, we know. And the question is find the maximum likelihood estimator for theta 1 and theta 2. Okay, so this is something you can try again, because these are random samples. So the PDF will be the product of the PDF. And in this case, you will see that it's better to use log likelihood. Okay, so you find a likelihood function. Okay, so the steps will be find likelihood function, and then the second step is that take ln of the likelihood function, and then maximize lnl, and the place where it gets maximized will be the same place at which the L will be maximized. Okay, so these are the few things that one has to take into account, and from there you will get the estimates for theta 1 and theta 2. In this case, what is even more is that you have like 2 parameters now. So it's like 2 parameter estimation problem. Okay, so that's why it becomes a little bit more more here. Okay, but it's possible to like do this. In this case, now you have to take partial derivative with respect to theta 1, and then you have to take partial derivative with respect to theta 2, and so on, and equate it to 0, and then from there you will get theta from the 2 equations. You will get 2 unknowns and 2 equations, solve for that. Okay. Okay. What are the properties of maximum likelihood estimators? So they are asymptotically consistent. So that's one observation. So we have seen consistent. So probability that theta had n minus theta greater than or equal to epsilon is 0, right? So that was the consistent. And here, see, this is what is the meaning of the consistent, asymptotically consistent. So that we have already seen before, and it is asymptotically biased. So if you take limit n tends to infinity and take the bias, then it is unbiased. Okay, you can also put theta on the right hand side, and then it is equal to 0. So that's like unbiased. And as n becomes large, theta hat ml is approximately a normal variable. Okay, so Yeah, because theta hat ml is a random variable in itself. Okay, so theta hat ml is a random variable in itself, and we know that as n tends to infinity, any random variable essentially behaves like a standard normal after doing some proper scaling. So that's thanks to the central limit theorem. Okay, so we do the proper scaling by theta and divide by the square root of this. So that's because of the yeah CLT, it will converge to the standard normal. That's the property of that. And then there is an example here that I can do in the next class, I guess. Yeah. So yeah, this is an example actually you can try. It's a very easy because the definition is given to you. So unbiased estimator of theta, right? And W is a zero mean random variable. Then so that this happens. Okay, so that this is an unbiased estimator for theta. Okay, so unbiased estimator theta. So you take a expectation of this minus theta, but then due to linearity, this expectation is zero anyway. Okay, and this is an unbiased estimator of theta anyway. So this also is going to be unbiased estimator of theta itself. Okay, because so what this says is that if to your unbiased estimator, you are allowed to add a zero mean random variable without changing the biasness, right? And similarly, you can try this. Theta 1 is estimator theta, and if it is of this form, then so that this will be an unbiased estimator for theta. Okay, so these are some simple applications of the previous result. Okay, so we can I can leave this as an exercise. Okay, this is okay, you can do this as an exercise. Okay, and then there is a solve example here. Okay, so I will try to do this solve example in the next class. Okay, so I think this is better. It is better to do this solved example in the next class. Yeah, so I think with this I will stop. And yeah, so remaining, so this I will try to wrap up, and then I will also discuss Bayesian inference, introduction to Bayesian inference in the next class, and that will wrap up our course. Okay, so these are easy topics. Okay, so you should not be tense. Okay, okay then. Okay, bye.